Hi everyone, welcome back. So let's try out some problems here. Some big problems. They gave us a book to read. What in the world? Well, we'll go through it one step at a time and then we can go from there. So what we have here is a 40 liter, electrical radiator right there. And that contains heating oil that's placed in a 50-meter cubed room. Both the room and the oil in the radiator are initially at 10 degrees Celsius. The radiator with a rating of 2.4 kilowatts is now turned on. Okay. At the same time, heat is lost from the room at an average rate of 0.35 kilojoules per second. After some time, the average temperature is measured to be 20 degrees Celsius for the air in the room and 70 degrees Celsius for the oil in the radiator. Taking the density and the specific heat of the oil to be this stuff. Okay. Determine how long the heater is kept on. Assume the room is well sealed so there are no air leaks. The gas constant of air is R equals 0.2897 stuff, and we also get some specific heats. Woo! My goodness, we got a lot of stuff to work through here. So let's make a plan. Well, the first thing we're going to do is write out our conservation of energy. Okay, so what's it look like? Well, I have E dot in minus E dot out, looks good, is equal to change in energy of my system. There's a dot there. So that's all fine. So first off, what energy is going into the system? Well, that's pretty simple. Only the radiator is giving energy into the system. Okay, so I can say that E dot in is equal to 2.4 kilowatts. Not too bad, not bad at all. Okay, now what is E out? Well, E dot out, that's going to be equal to my heat that's being lost. And that's going to be equal to 0.35 kilojoules per second, which is 0.35 kilowatts. Okay, so we got a lot of stuff going on here. This is looking pretty good. And as a note, just so you know, that I would be writing this as work dot. Then how about my energy in my system? What's changing here? Well, my system is oil and air. And so when I'm saying system here, if I wanted to write this all out, I could have written out delta E system like this. It'll be equal to the change internal energy of the air with time plus the change in internal energy of the oil with time. Why is it internal energy? There's nothing moving around here. There's no flow, and so I'm not going to worry about the flow work. Just the change in temperature. Now, if we're having specific heats in here, it gives a lot of specific heats, we can write this out even further. So we can say, okay, well, mass of air, yes, that looks good. Mass of air times C delta T plus mass of oil, C delta T. I need to make that sure that's air right here, and that's oil right here. Beautiful. Would be equal to it. Now, there is an issue here. Look at that M. Do you see a dot? You see no dot. Do you see a dot there? No dot there. Why? Because there is no flow right here. These are not flowing into my system. These are just stationary masses. And it's frozen on me. I think this will fix itself in a second. So I'm going to have to figure out how I can go from being just M to actually dealing with it in time. And there it goes. Well, how am I going to do that? Just divide it by delta T. That's it. It's not a huge issue. We just say there's a time frame we're doing this over, and it's all going to be fine. Okay, so with that, let's write it all out and get going forward. So I have work in, so I'm going to write it out just like in variables, and I'll write it out with numbers. So work dot minus Q dot, we'll multiply that by delta T. The reason I'm doing that is just so I can bring it over, is equal to mass of air, C air, and let's see here, I'll say this is delta T here. I'll give it as it is. Plus mass of oil, C oil, delta T oil. Okay. That looks, yeah, that looks really good. So what we're trying to solve here is how long the heater's been kept on. We have a lot of information here. We have, I'll highlight the things in green that we actually know. So I know my work, I know my heat, I know my specific heats, and it told me, let's see, yes, it told me what the temperatures were at the beginning, so I also know what the change in temperature is. So look in here, and what do you see that I do not know? I don't know the mass. So before I can solve this, I'm going to have to figure out the mass. Now, that's not terribly hard to do. We can do without too much trouble. Okay, so let's get into this. So first off, let's deal with oil. Now what do we know? Well, at first it tells us that the volume of the oil is equal to 40 liters. Okay. It also tells me that the density of the oil is equal to 950 kilograms per meter cubed. Now you're like, well, there's liters here and there's meters cubed here. I don't know the conversion for that. Neither do I. Now I could cheat and look it up on the internet, but I've got no way of doing it. Do I need to do it this way? No, I could just look up how many liters in a meter cubed or back and forth. It's fine. But I'm going to use densities that I know. I'm more or less using specific gravity to do this. So I know there's 1,000 kilograms per meter cubed. That's the density of water. I also know that density of water is 1 kilogram per liter. And so I can use it to actually cancel my units and translate it. And so I'll get that the density of oil in this case would be 0.95 kilograms per liter. So from that, I can calculate the mass of the oil. So mass of oil would be equal to density of oil times the volume of the oil, which would be equal to 40 times 0.95, and that would be 38 kilograms. 38 kilograms. Okay, so we have it. It looks good. So that's one more thing that I know. I got the mass of the oil taken care of. Now all that's left is the mass of the air. If I can solve for that, I am golden. So let's figure out the mass of the air now. What information did it give me? Well, it told me it's a 50 meter cubed room. Okay, so I'm going to put air over here. So once again, I have a volume. It's equal to 50 meters cubed. It also tells me that initially the air is at 10 degrees Celsius. Okay, so temperature is equal to 10 degrees Celsius. It gives me the specific gas constant of air, which is 0.287 kilopascals meter cubed per kilogram Kelvin. And nothing else on like the density side. If only there was like, ideally if there was an equation that could connect all these stuff together. This ideal equation. Oh wait, ideal gas equation. Air we can assume is an ideal gas. Why? Because it's not crazy. Like if it's at crazy pressures or something, then we can do this. But this is in a regular room, and hopefully this room is not pressurized insanely. So what we're going to assume here is that the pressure is equal to 100 kilopascals. You're like, well, how can you assume that? Well, I'm assuming it's atmospheric. Technically, atmospheric is 101.325 kilopascals. But just for the sake of making my numbers look nicer, I'm making it 100. Will it throw this off much? By less than about 1%. So it'll be a really small change. I think we can do that. And we know that PV is equal to RT. Or if I really want to make this work better for myself, P is equal to the density times the specific gas constant times temperature. So I'm going to plug that in. So I'm going to solve for density. So density will be equal to the pressure over the specific gas constant times temperature. That'll be equal to 100 kilopascals over 0.287 kilopascals meter cubed per kilogram Kelvin. Then finally times the temperature, which is not 10 degrees Celsius, this is Kelvin, it's 283 Kelvin. Now if I plug this in, what do I get? I get 1.231 kilograms per meter cubed. Oh, that's not volume. That's the density. Okay, and then from that, I can then calculate the mass of the air. So just like for oil, mass of air is going to be equal to my volume of air times my density for the air, which will be equal to 50 meters cubed times 1.231 kilograms per meter cubed. Okay. And what number is that? I don't know. I'm going to find out in a second. It is 61.56 kilograms. Okay. There's quite a bit of air in there. Now, since I have all of this, you might realize I know everything in my equation except for the time now. So if I want to figure out how long that was on, all I have to do now is plug everything in. So we're going to do that. We're going to plug absolutely everything into this equation. It's going to be a whole lot of numbers, and we'll get it. Now, here is the thing, and I want to stop you right now. For any problem like this, do not, under any circumstance, plug in everything into your equation. Like, even if I were to make a nice little, rearrange this equation right here, such that I have one nice equation, if I were to try to plug all those numbers into my calculator, I would probably make a mistake. It'd be very hard to figure out what the mistake is later. So I'm not going to do that, okay? What I'm going to do instead is I'm going to just plug in this section and get a number, and I'm going to plug in the other section and get a number, and I'll divide those two numbers, okay? It's not going to be that hard. So let's figure out what this guy is first. So let me plug that into my calculator and we'll see what it comes out as. Okay, so just for this first part right here for the oil, I got 5,016, and that should be in kilojoules. Okay, now I'm going to do it for air. If you're wondering how I did that so quickly, I'm pausing the video. I can do that. I've got movie magic here. So once again, let's try out for air now. Okay, and for the air I get a amazingly huge 0.116 kilojoules. Remember, air is not very dense. It doesn't absorb much energy. Okay, so with that, I think I could do the best of the math by hand. So let's kind of plug it in here. So I have 2.4, that is my power input, kilowatts, which are just kilojoules per second, just so you know, minus 0.35 kilojoules per second, okay, times delta T is equal to, really the oil is the only one that matters. I don't even need to include the air. I'm going to just be extra exact and add them both together. So I'll have 5,016.116 kilojoules. Now let's solve for delta T. As a note, everything inside of this guy right here will be 2.05 kilojoules per second. So delta T is going to be equal to 5,016.116 kilojoules divided by 2.05 kilojoules per second. Kilojoules is going to cancel, and I will have seconds after this. And how many seconds? Let's find out. And so what I get from this is I get a time of 2,446 seconds. There's an issue with this. That's wrong. You got it wrong, Dr. Kid? I did. And here's the thing. I already know where my problem is. Now, this is not because we had some horrible mistake all along the way. It's because of a calculator issue. And it's one of the reasons I wanted to show you the importance of writing out each individual step. Because I can look at this and immediately say that I wrote that math correctly. And I went and checked my calculator, and guess what? I got that one right too. But you know which one I plugged in my calculator wrong? this guy right here. I plugged it wrong in my calculator. So when I plugged it in, I don't actually know what I plugged in right now because it went horribly wrong. Should have been 61.56 times 0.718 times 10, which is 442. So that guy right there should not have been 0.116. It's 442. And so if I do that, and I actually plug all my math in right, I can get a better answer. So let's go through this again, being more careful with our numbers here. So 5, 4, let's see, 5, 8, that looks good. 5, 4, 5, 8, perfect. And finally at the end, what is the right number? That's a terrible 5. Let me rewrite that 5. Man, my second 5 is worse than the first. There we go. The final number should be the following. 2,662 seconds. Which if I divide that by 60, I get 44.36 minutes. Okay. So the moral of this story is make sure that you're taking intermediate steps, because otherwise you'll never be able to find where things went wrong, like I was able to do because I took it in so many steps and I was writing all this all out. So thank you all for listening. Hopefully this helps you, and I'll see you all next time. Bye-bye.